George for his magnificent invitation and reception, and for the fantastic working conditions we have here. It's a great pleasure and honor to be here for the second time. Okay, let me first, before I introduce myself, I will need a chairman to interrupt me after 1 hour, so we can use the half-hour discussion. So
we can have the mechanical
Basil. Yes, Basil, thank you.
Good referee.
All right.
A mechanical chairman.
Oh no, I prefer the other one there, the real one.
You have a pen now, or?
No.
Okay, I find it.
Okay, let me first introduce myself. Thank you. Thank you very much. Where's the device? The overhead projector. Okay, let me introduce myself first. I got my PhD at the University of Nice in 1978. Nice was at that time a stronghold of the famous Bourbaki school, and my supervisor was Jacques Chazarin, specialist in partial differential equations and pseudo-differential operators. I was his last math student because a few months after having supervised my thesis, he started working with artificial intelligence. My PhD was on partial hypoellipticity for pseudo-differential operators, Hermander's theory as it's called. I got my habilitation at the University of Paris 6 in 1992, under the mentorship of Jean Leray, which was a very famous French mathematician. I was the last person he supervised. He died a couple of years later. Actually, my habilitation was on a collection of papers I had written with Leray and papers I had written before. And actually, I was very impressed by Leray's work on the Maslov index and semi-classical mechanics. His work on so-called Lagrange analysis. And Leray helped me very much to understand things in his book. It took me actually 5 years to read the first chapter in his book, and I haven't finished it yet because it's very condensed and very, very complicated. And thanks to Basil Hiley, but I'm not his last student. Thanks to Basil Hiley, okay, my interest in mathematical physics and especially in quantum mechanics has been growing ever since. And I thank Basil very much for all his advice and help. Yes. Inverse, okay. Today I'm going to talk about, it's going to be much ado about nothing actually. About emptiness and phase space and uncertainty principle. Oh, I apologize, my transparencies were lost or stolen in the plane from Brazil to Europe, so I had to make a reconstitution today. So, but anyway, I'm a mathematician and of the old school, so I will use the whiteboard and body language to voice. Okay. My permanent affiliation, so to say, is at the University of Potsdam in Germany, and starting next month I will be in Vienna. I will work with the Feichtinger group on signal analysis or time frequency analysis, which is a version of quantum mechanics actually, quantum mechanics in phase space. And okay, I'm going to talk about Heisenberg's uncertainty principle from a symplectic point of view, from a topological point of view, so to say. And this will allow me to invoke the principle of the symplectic camel. We'll see why this is called the symplectic camel. And to produce some kind of quantum phase space, and there I would be very grateful if I got some response and criticism and perhaps encouragements and all this, because I'm not a physicist. I'm trying to be one, but And there's a fundamental link with all this, Bohmian mechanics, and I discovered this by reading Basil's recent paper. Where is it? Yes, it's here. On the relationship between the Wigner-Moyal and Bohm approaches to quantum mechanics, and by Basil Heilig. And this paper opened my eyes on the fact that Bohmian mechanics is already contained in the Wigner-Moyal formalism. So it would be also interesting to see in which way Heisenberg's uncertainty principle could be used to derive or to study Bohmian mechanics. I don't know. So, well, let me first begin with some simple things from elementary geometry. I'm going to talk about phase-space ellipsoids. So what's a phase-space ellipsoid? I'm going to use the standard notations here. The x's are the physicist's q's, a position variable. And the p's are the momentum variables. I work in n degrees of freedom, that is the phase space will be R2n. Okay? Working 2n variables. And what's an ellipsoid in phase space? Okay? Well, it's a set Bn defined by a relation like this here. This is the equation for an ellipsoid centered at the origin in phase space. And more generally, if you center your ellipsoid at an arbitrary point, z0, the equation will be this here. M is a positive definite matrix, symmetric. That is, in addition, we have M equal to mt, and to say that this matrix is positive definite means that all its eigenvalues are real and superior to 0, or equivalently, this expression is positive, or 0 when z is equal to 0. Okay? A related concept which is extremely fruitful and interesting is that of symplectic capacity of a phase-space ellipsoid. Let me explain. I say that the symplectic capacity of any of these two ellipsoids is 2 pi over lambda, where lambda is the largest eigenvalue, or the modulus, or the largest modulus of the eigenvalues of the matrix Jm. What does this mean here? Okay, you know, there is a fundamental matrix in symplectic geometry, which is sometimes called the Weil matrix, or also the standard symplectic matrix. Matrix J here plays the role of the complex number I. You can see that by noticing that J squared is equal to minus the identity. And to this matrix, you associate an antisymmetric form, which is called the standard symplectic form. It's defined in the following way. Here, if I take two vectors, z equal to xp, z prime equals to x prime, p prime, well then, sigma of z prime is just z prime transposed j z. Okay? Or in coordinates, if you prefer, this is just p dot x prime minus p prime dot x, where the dot is the usual scalar product. Okay? This is a bilinear form. It's linear in both z and z prime, taken separately. It's antisymmetric because if you switch z and z prime, then this thing will change sign. Now, notice that in the case n equal to 1, this is just minus the determinant, okay, the usual determinant. Okay? And in addition, it's non-degenerate in the sense that if this is equal to 0 for all z prime, well, then z must also be equal to 0. Okay? So it's a kind of scalar product. It's not a scalar product, actually. No, it defines a structure which is called a symplectic structure on phase space. And the symplectic structure is essential in understanding Hamiltonian mechanics, for instance.